a life-sized game of Operation, the first Avengers 3D printer, magnetically aligned resin, and 3D printing with a hydraulic press. There you are. Welcome back. It is episode 3 of our 3-episode coverage of RAPID TCT 2021 from McCormick Place in Chicago, Illinois. Thanks to SME. You've seen episode 1. You've seen episode 2. Now, for episode 3,
don't try it.
We've got on board Stratays. We've got on board LDO, but it's actually Dave from Printed Solid. We've got 3D Fortify, and we've got Impossible Objects. 4 different booth visits that you are going to be incredibly excited to see. And first up, Stratays. A trip to RAPID TCT 2021 wouldn't be complete without a stop at the Stratays booth, and it's exciting because we've got the game of Operation supersized, and I've got my friend Evan here. Hey, Evan.
Hey, thank you for having me.
Thanks for stopping by. I figured a challenge is best because there's a lot of really cool 3D printed things in here that I'm told you can talk about.
Oh, this is my favorite game right here.
But you can only talk about them if you can successfully remove them from the game.
All right, all right.
Now, just to show them and you and me,
there goes that light.
it is active. So Evan, I hand the salad tongs.
We'll go with salad tongs, yes.
Okay. Okay, where are we going first?
All right, so we're going to start down here at the Charlie horse. You know what a Charlie horse is?
It's when my kids hit me really hard in the leg.
Your kids hit you really hard in the leg, you have a leg cramp, one of those. This is my favorite model right here.
Ooh.
I love this model.
So what makes this your favorite model?
It's printed on our RPS technology, so it's stereolithography, vat photopolymerization. It's a clear material, and it just looks beautiful. Look at how stunning the main is through here. This has been in the booth all day. People have been trying to operate this all day, and it still maintains those material properties, has that beautiful look to it.
It's rigid, it's resilient, it's been operated on.
Yep.
The Charlie horse, I really like that. Well then, let's set it up here.
Perfect.
Where are we going next?
We're going to do the femur next.
Ooh, the femur. That's a leg bone, if I'm correct.
It is the leg bone, and the femur is actually the tibia in this case. We have this mixed up. Our operation patient is not doing too well yet. So we're going to take the femur out of the tibia slot.
Okay.
Let's see if I can do it. All right.
Hey, look at that. Wow, that is bone white.
Good one, good one.
I try.
So I really like this model too, and it's really unique because if you were to actually cut in this model, you know what it would feel like? It would feel like a real femur bone.
Would it really? This is a bone analog?
Yeah, take a look at the end of it. You see how it has bone marrow? It's actually
It's got
squishy.
marrow. Yeah, it
has
feels
marrow.
squishy. Oh.
So in medical terminology, it's got a cortical shell, it's got a cancellous interior, and it's got bone marrow going throughout it.
Okay, so then training.
Yep.
Oh, cool.
So we see these being used before surgical practice, so pre-surgical training to make sure that we are going to perform that surgery appropriately.
That's important because being able to practice a surgery that gives you the conditions as close as possible to the actual patient you're going to operate on ensures more success.
And this is 3D printing, so we can really 3D print whatever we want, including that patient-specific anatomy. So instead of practicing on a one-size-fits-all, we practice on a real patient, but a simulated real patient.
That's, well, simulated, but in real life, so instead of digital. Okay, okay. That's kind of cool. So now we've got more. Where do you want to go next?
I want to do the love handle.
The love handle?
The love handle.
I see that.
We've got 2 of them. I'm going to do the one that's closer to me because less of a chance of me failing.
That's a really good point, okay?
All right, here we go. All right.
You are skilled. Oh, it's light. I was expecting, it looks metallic. I was expecting heavy.
It's a super light material. It's actually a nylon 11, so PA11,
PA11.
polyamide 11, whatever you want to call it. It's a powder-based process. So it's actually coming from Stratays SAF technology or selective absorption fusion. It's very similar to a powder bed. Well, it is a powder bed fusion process. So we're actually jetting out liquids using inkjet print heads, and then we're essentially thermally heating those up, causing the material to fuse together until we get our model.
Oh, okay. Wow, it feels strong, but it's got a little give to it.
It
so
does.
It's not stiff.
So you know where this fits really well in the healthcare industry?
No, where?
Orthotics and prosthetics.
Oh, anything that's going to go close to the body, you want it to have a little bit of give, right?
A little bit of flex, a little bit of give to it. It's going to work really well, especially for young adolescents, pediatric patients, because it's super cheap to print. and you can continually iterate as that patient grows.
That's great. So anything that makes healthcare less expensive is a huge positive. All right, Evan, where are we going?
All right, let's do, we'll do the tibia, but in the femur slot next.
Okay.
This one's gonna be a little tough.
Oh! I'm sorry, the rules is as rules is. Rules is as rules is. All right, well, the tibia and the femur, I'm sorry. I'm sorry.
It's all right.
We can't actually talk about that. But there's still plenty more to play for, Evan. Don't get discouraged.
All right. We're gonna go.
I don't want to make you anxious. I'm sorry.
So we're gonna do the next one. It's gonna be the rib.
The rib. Ooh,
this one is the toughest of all the models here.
Yeah,
So
I would imagine.
It's got such a narrow access point.
Oh my goodness.
And we got it.
Wow. Oh, I was rooting for you, my friend. That was amazing.
Thank you.
So this feels similar in texture to
the bone.
The femur, right? The femur. Yep. Yeah. Okay.
So this is very similar to the femur, but this is a rib structure. So it's going to be slightly different in structure. If you were to take a rib out of your body, hopefully we never have to do that. This is going to feel exactly the same. So give it a bend.
Like a.
Just a little bit.
Okay.
You can see how it's flexible.
Oh yeah. Well, ribs are a little bit flexible themselves, right?
They are. They've got a lot of cartilage in them that helps bend, especially as we get closer to the sternum. You have cartilage connecting the ribs to the sternum being the center of kind of your chest. Mm-hmm. So go ahead and bend that a little bit more. See if you can get it to break.
Oh, it's not breaking.
Yep.
Okay.
I
was super worried for a second.
To it. Yep.
Wow. Okay.
So this is printed on a material jetting system. It's a polyjet system. Same system we had with the femur bone. Just again, a little bit of a material combination. It's got that bendiness to it. That's going to more accurately replicate a rib structure.
That's okay. That's really cool.
Yeah, I love that sort of
stuff. I
was
was really worried, honestly, because I wasn't sure.
That's okay. I've done that to multiple people today.
I would imagine.
All right, so next we're going to hit the eyeball up.
The eyeball.
See the eyeball in there?
Okay, yeah, I do. I don't know how you're going to get that.
Just a steady hand and some luck.
Oh,
and we got it.
Oh my goodness. Look at that. It looks like well, I mean, I know it's not a glass eye, but it looks like a glass eye.
It has depth to it.
Yeah.
So this is utilizing, again, material jetting technology, same as we had with the rib and the femur from earlier, but we're using rigid materials and only rigid materials. We can actually use what we call voxel technology. So I always talk about Minecraft, Lego blocks.
Oh yeah, 3D pixels.
Yeah, 3D pixels.
Yep.
And that's what we use to create this. So there's actually depth to the eye. So as you look into that iris, as you look into the eye, you can actually see the inside of the eye. Yep. Take your flashlight out, see what you can do.
Oh, look at that!
Yeah, you can see actually you can see from the back. I know you can't, but you can actually see the light go through and hit where the cornea is.
Oh, that is cool.
Oh yeah. This is one of my favorite models. These are all my favorite models. I'm going to keep saying that, but
you have a lot of favorite models. But that's okay. Okay, that is cool.
Yes.
That is cool.
All right. Let's do the heart.
All right.
The critical component of the human body.
It really is.
This one's easy because
that's really it's only half a heart.
Yeah, it's half a heart. So it's showing you the interior of the heart. It's soft. It beats.
It does.
You can actually flow water through this stuff.
Oh, okay.
It'll beat like a real heart.
So now there's a different hardness here. This is soft. This is not as soft. Is that just because the thickness?
Yep.
So
we can value the softness versus hardness, what we call Shoreline scale.
Yep.
But in this case, it's just with the geometry itself. The thickness of the model is going to cause some to feel more rigid and some to feel less rigid.
There's valves. I mean, you've actually got valves in there.
Yep.
This is really cool.
So we've designed it to be exactly like a human heart. We're using myocardium. We're using some vessel materials. We even have annulus and the valve materials are in there are specifically meant to be like real valves in the human heart.
I recognized a couple of those words. Okay, I'll tell you what. For the sake of time, we've got one last one, and I'm kind of hoping you pick this one because it looks amazing.
I'll do that one. That one's really hard to get out of there because it's such a heavy model. So you know what? How about you do this one? Let's see if you can do it.
Savage. Okay.
Do you have the skill to be a surgeon?
I don't. I understand. Okay.
I think you could do it. I think you got it.
So,
watching the red light over here. Oh, he's got it by the finger. He's pulling it out. All right.
Okay, legit, right? Legit.
Woo!
That was actually, because, I mean.
That was some skill right there. You might have the ability to be a surgeon in the future.
I appreciate that. I'll tell you what, I'm going to leave right now and start medical school. If I look at this, it's not just like it's a bunch of neat, like when I do multicolor 3D printing, it looks cool, but it doesn't look like this. So why does it look like this?
So this is, again, another material jetting polyjet model using full color. And we print it all at one time and give it this nice color look to it using different photopolymers, different types of ink, essentially, to give it that nice, vibrant look. And then it doesn't come off the printer looking like that. I always like to show this. This is not what it looks like after you remove support.
Oh.
It's one of those marketing models that we make it look really nice.
Okay.
But we've actually sanded this down, clear coated it, buffed it a little bit to get it to look like this.
How much time would you say went into making it look like this from the print bed?
About an hour.
Oh, that's not bad.
That's not too bad.
Okay, but I would imagine this is great, especially since we're talking about medical as a teaching tool, right?
Yeah. Oh, absolutely. Being able to talk about the complex properties of each area of the human hand, this is a huge teaching tool. I mean, you think of what we've been able to communicate in the past. Yeah, sure, we've had some urethane casted models like this, but now we can have this model right next to an exact same model, but using functional materials. So we have our visual model to teach the students where to maybe cut or suture. But we also have a functional model right next to it that we can actually suture, that we can actually cut into and see how it operates.
Well, what I like is this material that's clear shows that there are parts in air, essentially showing depth and space within the hand. And so that's probably really important.
Yeah. It's important to understand. We actually made the skin clear and everything else on there is.
Yeah, you did. See, it's normal skin here, but it's, oh my goodness! Hey, Evan, this has been a lot of fun. I want to thank you for giving us.
Absolutely, thank you.
Congrats on playing a mostly successful game. I'll tell you what, if people want to know more about all of this cool stuff, is there a specific place they can go to find it?
Stratasys.com/medical.
/medical.
/medical.
There we go. I'm at the LDO booth at RAPID, but this isn't Jason. David, why are you here?
Well, as you know, we sell a lot of the LDO products.
Yeah.
But LDO works with the VORON groups, well as we do that as well.
And that's why we've got this little baby VORON right here, right?
The VO.1.
It's so cute. It's so cute.
And this is the one that I built. I actually did a live stream of it and built this on one and a half goes on the 4th of July this year. It's called the Steve Rogers.
Of course.
It's built on the 4th of July. It can do this all day, and it has a draft shield.
Oh, a shield, huh?
That's right.
Look at that. Did you leave milk and cookies out for Captain America when you were building this?
Pretty much.
So this is a little baby VORON, a VO.1,
yes.
right? And what makes this such an attractive kit?
People want to play with Core XY.
Okay.
People want to have another printer. This is a very small printer. We're talking 120 by 120 by 120 build volume.
Okay, okay.
With a Core XY technology, running Clipper, so you're going to get really fast print speeds. Some people have claimed up to 1,000 millimeters a second.
Sure.
And it seems counterintuitive, but it's as far as small printer, why does it need to be fast?
Yeah.
But it actually makes a lot of sense. I mean, I'm printing surprisingly slow right now on this printer, and this is a 4-hour print that's coming off of it right now, and this is an 8-hour print.
You could do that a lot faster if you wanted to, right?
I've been able to print this out in 2 hours. When I kind of haul butt on this and get to town.
Well, what's really neat, I like to think that as a smaller 3D printer kit, it's a way of getting your feet wet into Core XY, Clipper, VORON design, all of that sort of stuff, because this isn't the last one you will build, right?
This is the one that's going to be on your desk.
Okay.
And if you look at VORON and all of the 3D printed parts, if you're going to build one of their bigger printers, all of the parts can be printed on this printer. I'm just saying. They thought it out. They're very smart on this.
That's amazing. So then obviously, we're at the LDO booth. You're here at the LDO booth because much of the parts here that aren't printed are sourced from LDO Motors, right?
Not only that, but LDO Motors has the full kit with everything except the 3D printed parts in it.
Oh, I may have a box at home from Jason from LDO.
You're going to have to thank him for that one.
I will. Thanks, Jason. Dave, I'll tell you what I really want to do, tell me 5 things you love about this machine. Go.
All right, first thing I love about it, one is size.
Size, you like the small size?
It's like the small size.
Okay.
It's perfect for ABS.
Oh, ABS, there we go.
It's perfect for that.
It's for printing the bigger VORON parts too, right?
That's right.
Okay.
3 is going to be the motor sizes. They're adorable.
Oh, well, they're This is a standard NEMA 17.
That's your normal NEMA 17.
Okay, this is a...
That's your NEMA 14.
And those are going to be right there and there?
That's your X and Y and the Core XY configuration.
Now this is interesting. What is that?
That's your NEMA 34 configuration, and that's what's driving the extruder. It's got enough torque in it to run a set of Bondtech gears.
Oh.
Direct, with no gearing.
Okay. So I think that's 3.
That's 3.
Okay, okay.
The fourth one is that it's open source.
Open source,
I'm
gotta
a big
love that.
open source
yes,
guy.
I rightly so.
And then shamelessly, the fifth one is, it's available at printedsolid.com.
So people wanting to know more about this, maybe pick one up themselves, they can go to printedsolid.com. What's the price on a VO.1 kit?
Retails for $650.
$650, get you the kit, get you the experience into the VORON design, into clipper configuration, into possibly making a replica of Steve Rogers.
Yes, this is what I'd consider a plus build.
Okay.
So it's one step above a Prusa as far as the complexity of building one.
Okay.
So not crazy, but about one step above it. So.
Okay, but still less complex than a VORON 2.4.
Actually, here's the humor of it. The V0 is the hardest printer out of all the Vorons to build because it's so small.
Oh.
I mean, they all have similar components, but it's so small, it's very hard to build. Just because I got big hands, and it's a pain in the butt to work in such a small space.
Okay, well then, hey, this is actually a great opportunity for young children to get their hands dirty and maybe build something and get used to this, because a lot of what I see here is applicable to all of these industrial machines that we see on this show floor.
Absolutely. This is a very realistic one, and I put it up against some of these industrial machines as well.
Yeah.
So, by the way, the quick little story I'll tell you on the end of this, there's a top hat that belongs to this. It's 3D printed. You can print it out as 2 parts on a Prusa.
Okay.
And it has acrylic sides and all that stuff on it. This is supposed to be on here. I put it on top of my car when I was filling up for gas and forgot to take it off, so I saw it flying off the road on my way here and land and get run over by a semi.
You saw it leave the roof of your car.
In my rearview mirror.
And so for a split second, you're like, oh crap, I have to pull over.
I pulled over, I was heading back, and then I saw the semi run over it.
I'm sorry.
Yes.
Dave, this was fun. It's always good to see you, man. Hey, Jason, thanks for bringing Dave. I appreciate that. All right, and if they want to find out more, obviously, printedsolid.com, go get themselves a kit, right?
Absolutely.
Well, out last night, a friend said while you're at RAPID TCT 2021, you have to go to the Fortify booth because they have incredibly cool stuff. And we came over here to find my friend Phil. Hey, man.
How you doing?
Doing great. So is it true? Is there cool stuff here?
Yeah, there's a lot of cool stuff.
We're standing next to this machine. I would imagine this is part of it.
This is exactly part of it. Yeah, what you're looking at right here is a Fortify Flux 1.
Flux 1.
That's right.
Flux 1. It's a fun name. Why is it called a Flux 1?
We named the series after our ability to introduce magnetic flux to align particles in the material.
Magnetic flux?
That's right.
Okay, that sounds really cool. What exactly does that mean?
Okay, so in this machine, there is one electromagnet that allows us to align magnetically alignable fiber particles in the resin in the z-axis direction while you're printing, so that we can reinforce components in the photopolymer.
Oh, so in the resin itself, the particulates that you're aligning, then when you use the magnet to align them, the magnetic field makes them all go in the same direction.
Yeah, that's correct.
Stronger.
Stronger is one aspect,
okay.
Yeah. So this material we have in the machine right now is our digital tooling resin. And we align the fibers in order to reinforce the components we're printing to make them stronger and more resilient to the hot thermoplastic resin we inject into the mold tools.
Oh, so injection molding, normally an injection mold is CNC milled,
yeah.
And it's metal, and it costs a lot of money,
That's
right?
right.
And it takes a long time to do.
Long time, yes.
So then you're able to defeat a lot of that.
That's right. So the machine, you can print an injection mold tool overnight. And then the next day, you have a mold tool that you can you have to do some post-processing, but you can put into a mold frame on an injection molder and make parts within 2 to 3 days.
That's incredible.
Yeah.
I would imagine a business that would use something like this is someone who needs to do iterative design on their molds or needs to be able to have a functional mold really fast.
Really fast, and also you can do low volume production as well. So we're talking about folks that want to do tens to hundreds of parts. You don't want to go to an aluminum tool for that because you're going to be waiting 4 to 8 weeks. you're going to have to engage with a third party, and you're going to have to maybe do some tool iterative design on that aluminum tool.
And you're going to have a lot of zeros in your account leave, I would imagine.
And so if you have one of these machines, you're working with somebody who has one of these machines, you can design your injection mold tools, you can get parts off, and then you can redesign and get parts off, and you can redesign and get parts off before you even get your first mold tool from your CNC manufacturer.
Do we have any pieces that this machine has made that we can take a look at?
Yeah, let's go over here.
What am I holding in my hand, Phil?
All right, so what you're holding in your hand is an injection mold tool manufactured out of our digital tooling resin. This resin is filled with a small volume percent of ceramic fiber filled particles that have been aligned using our flux alignment technology. And so what you're feeling is why it feels so robust and why it feels so strong is because it's loaded with ceramic fiber.
I see. Well, it's heavy too.
Yes. And if you tap it on something, you can hear the difference. Like, it doesn't feel like polymer.
Oh my God! It feels like just a solid chunk of something.
Yeah, that's right.
So then this.
It's a you got the slide out there.
Hey, look at that. So this is for injection molding.
That's right. And so you can take a part like this, and you can make a part like this. But you don't just make one. You can make tens or hundreds, depending on the type of material and the complexity of your geometry.
So something like this, if I were to do this via traditional methods, it would be most likely cost a lot and take a couple weeks, made of metal, and if I had to change anything about it, it would be a long wait time. Yeah,
you'd have to send it back to the manufacturer.
Okay, so then this is allowing, like you said, the small batch manufacturing. This is allowing very fast turnaround, and the feel of it is unreal. Like I've printed in resin parts before, and this doesn't feel anything like that. What else can you show me that's cool?
Yeah, let's go look at some of our other applications. So we're also working on, I'm going to talk about these two materials here.
These two right here, okay.
So this material right here is our thermally conductive dielectric material.
Thermally conductive dielectric.
Yes, that's right. So what that means is that this is an insulative material, electrically insulative material, but it conducts thermally. So typically you get both together, right? You're thinking about copper, you're thinking about any of your metallic elements that you use for heat sinks.
Right.
Exactly. And so what we're looking at here are heat sinks manufactured from a dielectric material that's thermally conductive. It conducts the heat, but doesn't conduct the electrons.
So then, using this material, what we can do is create geometry that sinks away heat in electric applications. So are we talking like transformers and grids?
Like electrical connectors.
Oh, just at that level?
Yeah.
Okay.
Yeah, you don't have to think too big, right?
I was thinking really big, but I mean, we're talking about everyday use items.
Yep, that's right. Well, yeah, I mean, they're highly technical electrical connectors, thinking about like automotive,
Sure. I get the idea, but I mean, I was thinking power pole, grid level, but we're talking about everyday use items, cars and automobiles.
Yes, that's right.
Just things that we see every day.
Combine that with 3D printing and making some really complex, high geometry is a lot of surface area. That thermal conduction is driven by the amount of surface area you have. So you can really drive up your ability to transfer heat by introducing more surface area through geometry.
There we go. So we can make the part more efficient in being able to sink away the heat digitally and then print it out, and so this would actually be more effective than like a copper counterpart.
It wouldn't be more effective, right? Because we're talking about something a little bit different. Copper is going to conduct electrons, and so we're looking for an alternative where we're trying to electrically insulate while thermally conducting, while also being thermally conducting. So there's a niche application space there.
It sounds niche, but I would imagine that this allows the ability to go into places where, like you said, copper can't go.
That's exactly right. Yeah.
I see.
Yeah.
So finally, I'm standing next to what look like microphones.
Not quite. Yeah. It does look like a microphone. You can. Yeah. It's not going to come off the stand, but you can pick it up.
Oh wow.
Yeah.
Did you guys glue it to the stand? Oh, you
I
did.
got a little sticky.
It's got a sticky there. Okay. So what is this?
Okay. So what we're looking at here is this element, this part right here, and this is a Leuenberg lens. And a Leuenberg lens is a concept that's been around since 1944. But it hasn't really been practical until recently. And what this lens does is it takes radio frequency energy and focuses it into a beam. And you might find this application in antenna systems.
Okay.
When you're trying to use higher frequency energy, that high frequency energy tends to attenuate, tends to lose all of its power as it goes through atmosphere, as it goes through water, as it goes through anything solid. And we need to take that energy and we need to focus it so it can go further, so it can without losing all of its signal.
I see.
Yeah.
So we're talking about in radio waves. So
Exactly.
like 5G faster, but it doesn't go as far.
That's exactly right. That's the trade-off. So 5G can contain more data because it's at a higher frequency and wider bandwidths, but the trade-off is that it's really hard to get it to go far. So we use something called directivity. We create beams of this energy rather than 4G, where all the energy just goes everywhere. You flood the zones with energy, with RF signal. With 5G, you have to make beams. In order to make beams, one way to do that is using a radio frequency lens.
Okay, so what would be the traditional way of doing this?
Typically, you don't focus.
Okay.
So in 4G, those radio towers you're seeing, they flood zones with energy, right? But if you want to focus a beam, you could also use a parabolic reflector dish, like your satellite dish, right? That's what those are.
Okay,
but obviously, this is significantly smaller, right? So there's a huge form factor savings when you go with lenses.
Oh, that's cool.
Yeah, and the reason we're able to do this is because we can process some really challenging materials. And our partners at Rogers Corporation came to us to help them to make low-loss photopolymers, and that's what this is, a very low-loss photopolymer.
What do you mean by low loss?
Yeah, that's right. So most photopolymers that exist right now in the 3D printing industry, photopolymers, things that go on DLP systems or SLA systems, have a lot of loss, which is a metric of how much energy, RF energy, goes into that material as it converted into heat.
Oh, I see.
Yeah.
I see what
And
you're
so
saying.
lower loss means that the energy goes in there and doesn't dissipate, and it remains part of that signal. And
I
so
see.
you can't make a really productive lenses unless you have a really low loss material.
That makes sense. And you are able to print them with that cool machine we
That's
saw.
exactly right, yeah.
This has been a lot of fun, Phil.
Yeah.
You know, if people want to find out more, because obviously this is pretty interesting stuff, where can they go to find out?
3dfortify.com.
3dfortify.com. Thanks,
That's right.
man. RAPID TCT 2021 is full of incredible things, and what better way to show that off than this table at the booth for impossible objects. I'm here with my buddy Thor. Hey, man.
Hey, Joel.
This is cool. A friend said stop by. They're doing incredible stuff, and this table is not disappointing. So if we were somewhere, such as an elevator, and I said, you've got 10 seconds, tell me what Impossible Objects does. What does Impossible Objects do?
Go. We are a 3D printer manufacturer where we are specializing with PEEK and nylon carbon fiber reinforced parts. So it's a PEEK part that's been reinforced every layer with that carbon fiber substrate.
Now, carbon fiber, a lot of times, so in my world with consumer-based 3D printing, we talk about chopped fiber, and it really, it makes a piece lightweight.
Yes.
It adds a look to it, right? It has kind of a matte finish, but I know chopped fiber doesn't provide strength.
Right.
So this must be different.
It is completely unique to the 3D printing scene where it is a long fiber. We're 1/2 inch and inch long fiber strands scattered throughout an unwoven fabric. So we have our substrate sheets, which are a 12 by 12 or 12 by 8 format.
Okay, and then, now this is a fiber sheet, so
Yes.
this is what gets impregnated into the PEEK or the nylon.
Yes.
How is that done?
So the polymer particles will penetrate the page.
The polymer particles will penetrate, that's a lot of P words
Yeah,
there.
I like that, that's my warm-up.
Okay, but I would imagine you've got something that sticks the polymers to the sheet?
Yes. So the sheet gets loaded one at a time, where it will pass underneath an inkjet solution. So we are printing out using an aqueous fluid, a 2D slice of your 3D model onto every single substrate. We then pass that sheet through a powder unit, that middle section of the machine, where we flood the entire sheet with our thermoplastic, whether it be PEEK or nylon 12.
Ah, okay. Okay.
And then we selectively remove all of that polymer that has landed in an unprinted area and can recycle it through the system to be used on the very next page.
Oh, that's cool. Okay, so there's not a lot of waste in the material, whether it be PEEK or nylon.
Absolutely. And it all gets recycled through the same system at room temperature, so there's no heat cycles involved. We then pass the sheet along through the end of the system and can stack them up using our registration pins. That is it for the printing solution. I like to use the analogy that the plastic will adhere to the sheet as if it were glitter landing on top of glue.
That's perfect.
Thank you.
That's perfect. Okay, so the sheets themselves, so this is a per layer process.
Yes.
So essentially we've got that aqueous solution, so it's able to flood the sheet, and then you've got the powder of your material, but this means your parts are not only impregnated with those long strand carbon fibers, but at the same time, they are just 100% infill, so to speak. It is fully PEEK or fully nylon with carbon fiber.
Super dense parts. It is a 100% infill part.
So then you've got your layers. So this is the example right here. You've got all your sheets of carbon fiber. You've got all of your aqueous solution, nylon or PEEK powder covered parts, and you've got your registration marks holding it all there. How do you turn that into like one of the parts we see on the table?
Yes, so we will take this printed stack out of the machine and bring it to our heated hydraulic press.
Heated?
Yes. So we will heat the entire build up to that melting temperature of that thermoplastic, at least 343 degrees Celsius.
That's really warm, and under pressure too.
Under pressure, inside of this hydraulic press. We will then compress it down to its nominal build height, and once it's cooled down, we will remove it and bring it over to our media blaster, where we will sandblast away all of the unbound fibers.
Oh, I see. So this is the example piece here, and everything in between this is just, would you say unbound, is that right?
Yes.
Okay, so then like sandblasting.
Like sandblasting. It's kind of like archaeology out of this build block.
It's like Jurassic Park up in here, right?
Right.
I have a really good question though, because this doesn't seem like a precise process. And so what is your precision for the parts that come out of this process?
Right, so our standard is 50 micron layers for the final compression, but we have experimented with higher. It is achievable. As well as we print with a 600 DPI on the inkjet print heads.
Oh, I see. So it's 600 DPI. It's almost like your pixel resolution if you were a resin-based 3D printer.
Exactly.
But I mean, it looks like does this pop out here?
Yes. Yeah, that was.
So I mean, that's pretty precise right there to be able to get this sort of part.
It's snappy.
Snappy. I like that. Well done. Good dad joke there. This though looks fairly clean. What sort of cleanup is needed besides hitting it with sandblasting?
Oh, you're looking at it. So this is
it?
This is it. This is the final product. It's come out of the press. We've sandblasted it away. We can add a dye. We can put it in our dunk tank. Our dye tank, rather.
Dunk tank. We've been to the carnival. I know what that is.
Yes. And this is really it. So sandblasting is really all it can take, or all it takes to get a final product. But we can also tap directly into the printed pieces if you want to insert screws or even insert threading. We can print threads. It is achievable. As well as we've gotten some really nice bike pedals.
Well, this is one of them right here.
Yes, absolutely.
Well, first of all, this is a drone body, right?
Yes, and we have a drone chassis up here as well.
I would imagine this is perfect for something like that because the piece is beyond strong.
Oh, yes.
And I'm going to knock it over. And it's incredibly lightweight. And then the bicycle pedal too. When you're bicycling, you want to have a lightweight bike, but you need it to be reinforced. I know a lot of carbon fiber comes into play. Absolutely. David, feel this.
Nice.
My producer David likes to ride bicycles, and he goes for miles and miles and miles. And so something like that, he understands that's amazing, right? Being able to do that.
It really is. And we do have a tested product in our display case.
Oh, fantastic.
Where, David Movitz is taking it on the trails.
So then, last question.
Yes.
And it's probably the most important one because it's a cool process, but is it phenomenally expensive, or is this something that someone who focuses on traditional manufacturing can look at maybe using in the future?
Sure. Yeah. So the printer itself is $250,000.
Okay.
And then the turnkey solution with the heated hydraulic press, as well as the media blaster and materials, turnkey is $350,000.
Oh, I see.
Yes.
Okay. So then, but the idea being a business that would use this has specific needs that these would fulfill, and they would have a timeline for when they would that that they would have the product sold enough to be able to pay off the device. Okay.
Exactly. We also offer a short-run printing service where we can print client jobs in-house for testing and qualifications.
Okay,
Yeah.
that's good. So people can actually test it out to see if this is something that would serve their needs.
Exactly.
Thor, this is amazing, honestly. Like, this is the next level stuff that you hope to see at RAPID TCT, and I'm really thankful I found your booth. If people want to find out more,
Yes.
where can they go?
Yes, so it's impossible-objects.
Ooh, a hyphen. Okay,
Yes, there's a hyphen in there. There's a
Impossible-objects.
We'll
put it on the screen.
Excellent.
Yeah,
Thank
yeah. Like all good things in life, unfortunately, we must come to the end. And this concludes our 3-episode coverage of RAPID TCT 2021 at McCormick Place in Chicago, Illinois, thanks to SME. All episodes 1, 2, and 3 are all in a playlist here. Feel free to share them with your family, your friends, or anyone else you might think is interested in the professional and industrial side of additive manufacturing. I had a great time. So did my team, and I'm really looking forward to the next show that we get to bring you some incredibly cool and possibly exclusive coverage. One thing I do want to mention, of course, we couldn't visit all of the booths. It was just impossible, even given the days that we were there. But we've really made a name for ourselves, and there were a lot of excited companies waiting to talk to us. And while you might not have seen some of their stuff in these videos, you can bet conversations are happening, and we've got some incredible things to show you. If you made it this far, you're awesome. Don't forget to hug each other more. Fight for a cause you believe in, print all the things, and as always, high five.